Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Since the dawn of time, mankind has sought an answer to an undying question. Are we alone? Now, humans possess the technology to solve this mystery, and we will shift their gaze to the stars. This is the search for exoplanets. This is TESS.
From NASA's Kennedy Space Center in Florida, you're watching live coverage of the Transiting Exoplanet Survey Satellite, or TESS, a mission to find new planets outside of our solar system that could support life. Hi, I'm Marie Lewis. Thanks for joining us. TESS will help us answer an age-old question. Are we alone in the universe? The images TESS will capture could be the key to solving the mystery. TESS is a planet hunter, about to embark on a 2-year mission to scan almost our entire sky by breaking it up into 26 different sections. Powerful cameras on TESS will stare at each zone for about a month, monitoring more than 200,000 stars and looking for changes in their brightness that signal a planet crossing over. Our goal is to find other planets like Earth and decide which ones deserve a closer look. TESS is scheduled to launch on top of a SpaceX Falcon 9 rocket at 6:51 tonight, Eastern Time, from Space Launch Complex 40 on Cape Canaveral Air Force Station. TESS has a window of 30 seconds to launch and will take 2 months to reach orbit. Coming up, we'll hear from SpaceX at its Mission Control Center in California. We'll also share more about the thrilling discoveries TESS could uncover. But first, we are now about 20 minutes from launch, so let's check in with NASA's Josh Finch and Mike Curie in Kennedy's Mission Director Center for a weather update. Guys?
Thank you, Marie. I'm Josh Finch.
And I'm Mike Curie, and we are in the Mission Director Center in Hangar AE on Cape Canaveral Air Force Station, very close to Space Launch Complex 40, where the Falcon 9 rocket is poised for launch today. We have teams from SpaceX, NASA, and the U.S. Air Force working from the east coast of Florida to the west coast of California to launch NASA's planet-hunting spacecraft. Our first launch attempt on April 16th was scrubbed to allow launch teams to further review data for the SpaceX Falcon 9's guidance, navigation, and control system. And that analysis is now complete, and we are go for today's launch at 6:51 and 31 seconds p.m. Eastern Time.
Marie, you asked about the weather for today's launch, and the forecast has improved as well from our first attempt. Today, the skies are clear, as you can see on your screen. The temperature is about 72 degrees, with light winds out of the southeast at about 10 to 15 miles per hour. We have no primary concerns for launch today. Our probability of violation is less than 10%, meaning we're over 90% go for today's launch in terms of weather.
The U.S. Air Force is also monitoring the eastern range to make sure commercial and personal aircraft are clear of the restricted area and that waters within the launch safety zone are clear of any boats. We also received a collision avoidance update, which is tracking any potential objects in space. It's all clear for today. We have no so-called COLAs, so we're on time for the opening of the launch window.
Teams continue to work through the necessary procedures to prepare the Falcon 9 rocket and the TESS spacecraft for launch, including loading fuel into both rocket stages and making sure all systems are properly checking out. As Mike mentioned, we've done collision avoidance with the Eastern Range, a checkout of the Autonomous Flight Termination System, and the loading of RP-1 fuel, our rocket-grade kerosene, began at about T-minus 1 hour 10 minutes. The Eastern Range confirms that it is go for launch of the Falcon 9 and the landing of the first stage, and liquid oxygen began being fueled at T-minus 35 minutes. So with weather a go and things tracking on time here, Marie, will go back to you.
All right, thanks, guys. This is not the first time NASA has explored the possibility of other Earths orbiting distant stars. The missions of Kepler and K2 have found thousands of known and likely planets that forever changed our understanding of what lies beyond our solar system. TESS, a joint mission between NASA and the Massachusetts Institute of Technology, will continue this groundbreaking work. But TESS is different from Kepler in 2 important ways. First, TESS will cover an area of sky 350 times larger than Kepler. TESS will also look at stars up to 100 times brighter than those Kepler studied. This will show us planets closer to our solar system, making follow-up observations much easier. Using TESS data, missions like the James Webb Space Telescope can hone in on specific traits of these planets. Are they water worlds or perhaps big rocks like Earth? And could they support life? Scientists expect to find about 300 planets the same size as Earth or up to 2 times larger. TESS will be the first launch of its kind for SpaceX, and NASA is proud to be expanding our range of missions with our commercial partner. SpaceX's Brian Malstedt joins us live from their Mission Control Center in Hawthorne, California with more. Brian?
Hey everybody, my name is Brian Malstedt and I'm a software engineer here at the SpaceX headquarters in Hawthorne, California. Now, it is not every day that you can say you're launching a planet hunter, so today we're all very excited to launch such a cool spacecraft. Now, most of you have probably watched our launches to the International Space Station, or the ISS, but the profile of today's mission is quite a bit different. For our resupply missions to the ISS, Falcon 9 delivers Dragon to a low Earth orbit at around T plus 14 minutes, and then Dragon makes its way to the ISS about a day and a half later. Now, for today's mission, Falcon 9 will be delivering TESS to an elliptical Earth orbit, from which TESS will then move on its own power to its final lunar transfer orbit. Now, that mission profile just described is much like more of our geosynchronous transfer orbit missions or our GTO missions. Now, after separating from the first stage, the second stage will coast for about half an hour with the deployment of the TESS spacecraft at about T plus 49 minutes. Now, today, TESS is flying on a new Falcon 9 rocket, but we are planning to land and recover the first stage booster after today's launch so that it can be reflown on a future SpaceX mission. Now, for this mission, we will be attempting to land on our autonomous spaceport drone ship, affectionately named, of course, I Still Love You, and we do hope that the signal holds out long enough so that we can bring you live video of that landing attempt. Now, the drone ship is currently stationed out in the Atlantic Ocean waiting to welcome the first stage back to Earth at about 8 minutes after liftoff. And remember, landing the first stage is the secondary objective for today's mission. Our primary objective is to deliver TESS to orbit, and so far things are looking great for an on-time liftoff at 6:51 p.m. Eastern Time. Back to you, Marie.
Fantastic. Thanks, Brian. TESS is decked out with impressive equipment to carry out its mission. 4 spinning wheels allow TESS to turn and point at specific stars. 4 state-of-the-art cameras will look for changes in light that indicate a moving planet. Each camera has 7 stacked lenses to bring images into focus. A shade protects the cameras from the sun's heat. A computer inside TESS stores data, and an antenna transmits that data back to Earth once every 2 weeks. Now, interpreting the data is just as important as gathering it. NASA's Amanda Griffin is live at Kennedy's Turn Basin with TESS program scientist Dr. Martin Still with more. Amanda?
Thanks, Marie. Dr. Still, thanks so much for joining us here today. Can you tell us a little bit more about these exoplanets that we're hunting?
Sure. Our solar system has 8 major planets, including the Earth, of course, and they all orbit our sun. If we look at stars elsewhere in the galaxy, they also have orbiting planets, and we term those exoplanets.
And so how is TESS helping us study those exoplanets?
If you can remember, the Kepler mission is still operating, and its task was to determine how common planets were in the galaxy. And the answer is they're everywhere. They're all over the place. So that allows us to build and launch TESS and do a survey for the nearest planets around the nearest stars. Now, Kepler, because of the nature of its survey, while we're all excited about the planets and the planetary systems that it found, you'll notice that there was not so much, there's not so much of the story after the original detection, because those planets are so far away, we could not follow up and do more science. With TESS, these stars and planets are so much closer that we can then characterize, we can find atmospheres around these planets, characterize the constituents of those atmospheres, so we'll be able to do follow-up, and so the stories of these planets will continue on long after detection.
And so why do we care about these exoplanets?
Because it's our human nature to understand what the universe is. It's our human nature to understand where we came from, where we are going, and of course, are we alone? And the only place in the universe we know there's life is here on Earth. And so the most natural place to go looking for it elsewhere are exoplanets.
And so speaking of searching for it elsewhere, I understand that you're looking for at 85% of the sky. Where is that other 15%? Why are we leaving that out?
Oh, sure. It turns out that we're already surveying that 15% with the repurposed Kepler spacecraft right now. So we're saving our own time and energy to survey brand new parts of the sky.
Perfect. Well, good luck with today's launch, and we look forward to seeing what TESS brings back.
Thank you very much.
Back to you, Marie.
Thank you, Amanda. You're looking now at a live view of Space Launch Complex 40 at Kennedy Space Center in Florida with NASA's next Planethunter on top of a SpaceX Falcon 9 rocket. We are almost ready to launch the Transiting Exoplanet Survey Satellite, or TESS, into orbit. Hi, I'm Marie Lewis. For those of you just joining us on social media, welcome to our launch coverage of TESS, which could help us find other worlds just like Earth. TESS will spend 2 years gazing at almost our entire sky by breaking it up into 26 different sections. 4 powerful cameras will stare at each zone for about a month, monitoring more than 200,000 stars and looking for changes in their brightness that signal a planet crossing over. Our goal is to find other planets like Earth and decide which ones deserve a closer look. The SpaceX Falcon 9 rocket is set to lift off with TESS at 6:51 this evening Eastern Time from Space Launch Complex 40. We have a 30-second window for launch, and TESS will take 2 months to reach orbit. At T-minus 10 minutes and counting, let's go now for a status update from Josh and Mike in the Mission Director Center. Guys, how are things looking?
Thank you, Marie. Things continue to go well here in the Mission Director Center at Hangar AE for an on-time liftoff at 6:51 p.m. The weather continues to be very well. No clouds in the sky. A really beautiful night as the sun sets over the Space Coast. We have no chance for precipitation tonight, light winds out of the southeast. We are less than 10% probability of violation, which means we are over 90% go for today's launch.
We have received confirmation that the TESS spacecraft is on internal power. Preparations for engine chill to allow for fuel or propellant to flow through the engines will occur at about T-minus 7 minutes. Communication checks with the Eastern Range are set for T-minus 5 minutes. The strong back, which stands next to the rocket, will begin to retract to launch position at T-minus 4 minutes 50 seconds, and the Falcon 9 will move to internal power in the final minutes. So, Marie, as we approach launch a little more than 9 minutes from now, weather is go, the spacecraft and rocket are go, and we'll hand things back over to you.
Excellent. That's what we love to hear. TESS is the second in an action-packed lineup for NASA's Launch Services program this year. It's their busiest schedule in more than a decade, with 6 missions in 6 months from 6 different launch sites. In March, the program launched a weather satellite called GOES-S, which has since been renamed GOES-17. It will give us life-saving warnings about hurricanes and wildfires. The program is already gearing up for its next launch in May. That's a probe that will delve deep beneath the surface of Mars. Joining us live about 5 miles from the launch site is NASA Edge's Blair Allen with more on what we can expect this year. Hi, Blair.
Hi, Marie. Thanks so much. We're joined now by Chuck Tatro of the Launch Services Program, and they described your lineup this year as action-packed. 6 launches, 6 cities, 6 launch vehicles. Sounds more like a launch tour to me.
Well, it is. In retrospect, we've had busy years before, sometimes as much as 8 or 9 launches a year, but this one is definitely unique, particularly, Blair, because we have an interplanetary launch to Mars from Vandenberg Air Force Base. So that on an Atlas V as an interplanetary mission is really a unique for us this year. But 6 missions is not a lot for the Launch Services Program, but to be in 6 different vehicles is unique.
And that sounds, how do you plan for that? Do you just take it as it comes?
We pretty much just take it as it comes. We've launched as many as 9 missions in 1 year before. In a couple of years of our history, we've done 8 launches, and several years we've done 6, but we've never done 6 on 6 different vehicles from 6 different locations. So we do have to be flexible and nimble.
It's pretty impressive.
Well, it's exciting. We love it.
Well, tell me a little bit about the unique features of the Falcon 9.
Well, this Falcon 9, this is our second contracted Falcon 9, and as you know, they're leading the U.S. launch vehicle industry in being able to reuse a lot of their really expensive launch vehicle components. Of course, the first stage, and now they're looking at reusing the fairing calves as well. But this is their first launch also to a kind of a translunar orbit. Their other launches have been to low Earth orbit, or their one Falcon 9 heavy launch was to put Elon's Roadster on a path to Mars.
Well, you got to be prepared for anything these days, right?
Right, and we like that the launch vehicle industry is evolving very quickly, and we're glad that we can be a part of that.
Well, thanks so much for being on the show. That we expect a lot from launch services, but we expect a great launch today.
Thanks, Blair.
Back to you, Marie.
Thanks, Blair. We are now 6 minutes away from launch. Let's check back in with Brian at SpaceX Mission Control. Brian, how are things looking from Hawthorne?
Everything is great looking over here at the headquarters as the energy starts to build underneath me on the mezzanine here. Now, for those of you who may not be aware, the Falcon 9 uses a rocket-grade kerosene for its fuel. Now, Mike and Josh mentioned this earlier over at Hangar AE. We call that RP1, or Rocket Propellant 1. But in addition to the fuel, you need an oxidizer on board to combust, and for that, we use liquid oxygen. There's no oxygen up in space, so we have to carry our own, and we do so in a very cold, dense liquid state. The fuel and oxidizer for any rocket are collectively referred to as propellants, and as of right now, propellant loading for Falcon 9 is currently underway. We expect to conclude the propellant loading process at about T-minus 5 minutes, so just about a minute from now. We are launching from Space Launch Complex 40 today, which is located at Cape Canaveral Air Force Station. So we've got the Air Force's 45th Space Wing supporting the launch. It looks like the range is ready to go and is tracking no issues at this time. And finally, the weather is looking beautiful, as you saw on your screen. So at T-minus 5, with the rocket, the satellite, the range, and the weather all looking good, we are go for the launch of the Planethunter TESS. Everyone here at Hawthorne is extremely excited to be part of this mission, and we look forward to liftoff just a few moments from now. Back to you, Marie.
All right, thanks, Brian. As you heard, we are just about 5 minutes from launch. We're closing in on the final activities. So let's go back to Josh and Mike in the Mission Director Center to take us through the final countdown. Guys?
Marie, it's T-minus 5 minutes and counting. We want to welcome you, those of you watching us on NASA TV or on social media, for the exciting launch on a SpaceX Falcon 9 rocket of TESS, the Transiting Exoplanet Survey Satellite. Weather continues to be go. We're working no technical issues. Josh, can you tell us what's coming up between now and liftoff?
Sure, absolutely. And just a few minutes ago at T-minus 7, the Falcon 9's first stage engines were trilled prior to liftoff. This allows the 9 engines to be cold enough to safely move propellants through them. Shortly following, the Falcon 9 will begin to move to internal power, and the systems responsible for igniting the engines just before liftoff will be pressurized for launch.
The strong back, which is the structure that's just to the left on your picture, next to the Falcon 9, will begin to retract to its launch position momentarily. The thrust vector control actuators will be moved or gimbaled. This is the system that allows for control of the vehicle while in flight. That happens about T-minus 2 minutes, 55 seconds.
We are T-minus 3 minutes and 55 seconds from launch. And at 1 minute prior to launch, the SpaceX Falcon 9 computer will begin the final pre-launch checks. At T-minus 45 seconds, the launch director will verify go for launch.
At liftoff, the Falcon 9 will produce thrust greater than 5747s at full power. And after liftoff, the Falcon 9 will begin a maneuver called a pitch kick. At 10 seconds into flight, this move gets the rocket flying on its correct path.
At just over 1 minute into flight, the Falcon 9 will reach transonic speeds. The vehicle will pass through an area of maximum aerodynamic pressure called max Q at about 1 minute, 18 seconds after liftoff.
Just over 3 minutes into the flight, the Falcon 9 will have jettisoned its first stage, started the first burn of the second stage Merlin engine, and jettisoned the fairing covering the TESS spacecraft.
The second stage engine will complete 2 different burns before TESS spacecraft is separated just over 49 minutes into flight. At a mission elapsed time of just under 58 minutes, the solar array, which will harness the sun's power, will be deployed. Our live launch coverage will end there, but TESS will continue to fly to its desired lunar orbit about 60 days after launch.
At liftoff, you'll begin hearing a number of different voices on the countdown net calling out over the broadcast. SpaceX ascent commentary is performed by several different people. The propulsion engineer calls out propulsion events. The avionics engineer calls out avionics health. The range coordinator calls out Air Force satellite control network acquisition and loss of signal. And the ground station specialist calls out the SpaceX antenna acquisition and loss of signal.
We are at T-minus 2 minutes and 20 seconds to launch.
Everything proceeding normally. Strongback has been retracted to its launch position.
Stage 2 LOX load complete.
Liquid oxygen fully loaded on the second stage.
Falcon 9 is on internal power.
And confirmation that the Falcon 9 is on internal power. You are looking at a live view of the
Vehicles
fairing
in self-align.
encapsulating the
Ground
TESS
gas
spacecraft.
closeout starting.
The autonomous flight termination system will be verified ready for launch momentarily at T-minus 1 minute, 5 seconds. Gaseous oxygen venting from both stages of the Falcon 9 rocket.
AFTS is ready for launch.
The flight computer is now beginning its final pre-launch checks.
Propellant tanks pressurized to flight pressure.
Pressing for flight. LD, go for launch.
And the SpaceX launch director is go for launch.
T-minus 35 seconds and counting. Shortly, you'll begin to see the launch pad's water deluge system, dubbed Niagara, activated. It suppresses acoustic waves that radiate from the engine plume.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Status of stage 1.
Stage 1 propulsion nominal.
And the SpaceX Falcon 9 has begun the pitch kick maneuver.
Power telemetry nominal.
Just over 1 minute, the Falcon 9 will reach transonic speed and pass through max Q. That's the point where mechanical stress on the rocket reaches its peak.
Vehicle is supersonic.
And the vehicle is supersonic.
Vehicle has passed maximum aerodynamic pressure.
Just about a minute away from the next major milestone.
Begun.
Main engine cutoff, you'll hear the call MECO. That happens about 2 minutes, 30 seconds into the flight. Coming up on the 2 minute mark in flight.
We're about 30 seconds away from MECO. 1 second later, the first stage will separate.
Ten seconds away from MECO.
MECO.
And we have confirmation.
Stage separation confirmed.
And stage confirmation is confirmed.
You're looking at a live shot of the second stage single.
Stage 1 is energy split. Impact ignition.
And the second stage Merlin engine has ignited.
Standing by for fairing jettison. That is protected TESS on its way through the atmosphere. Just seconds away from jettison.
Fairing separation confirmed.
And visual confirmation as well of the fairing separation. About 5 minutes remaining in this burn of the Falcon 9 second stage.
Grid fin deploy.
We are at a mission elapsed time of 3 minutes, 33 seconds.
Nominal trajectories.
You'll hear calls about the first stage making its way back to the autonomous drone ship. Meanwhile, the second stage of Falcon 9 continues to carry TESS onward toward space. About 4 minutes remaining in this burn of the Merlin engine on the Falcon 9 second stage.
And there on the screen, you see the first stage of the Falcon 9 rocket coming back to the drone ship in the Atlantic Ocean. The second stage continues to burn. The second stage Merlin engine. About 2 minutes, 35 seconds left in this burn. And there's another shot of the Falcon 9 first stage. We're at a mission elapsed time of 6 minutes, 13 seconds.
Stage 2 continues to follow a nominal.
Stage 1 entry burn has started.
And the stage 1 entry burn has started. The Falcon 9 coming back to the drone ship in the Atlantic Ocean.
Stage 1 entry burn shut down.
And confirmation that the stage 1 entry burn has shut down. About 1 minute, 15 seconds left for the second stage. Burn until it's complete.
Stage 1 AFTS has saved.
Members of the TESS team.
In the Launch Vehicle Data Center at
Stage 1
Hangar
is
AE
transonic.
on Cape Canaveral Air Force Station.
And the first stage has just gone transonic. "30 seconds away from the second stage engine.
Stage 1 landing burn has started.
Stage 2 is in terminal guidance.
About 10 seconds left in the second stage burn. Here's a camera on the drone ship where the Falcon 9 first stage will attempt to land.
Landing legs have deployed. Falcon 9, touchdown. Landing operators proceed near 11.100 on recovery 1 net.
And the first stage is
Stage
landed,
2, AFTS has
and the
saved.
second stage engine burn has completed. And with the completion of the first burn of the second stage, and landing the Falcon 9 first stage on the drone ship, we will now begin to go back to Marie Lewis in the auditorium at the press site located at Kennedy Space Center. And Marie, we'll turn it over back to you.
An amazing sight to see. With the survey area spanning nearly the whole sky around Earth, TESS's cameras have a lot of space to cover. Carefully timed rotations will help TESS accomplish this extraordinary feat. Here's a video to show you how.
In the last few decades, we have found thousands of worlds around other stars. A new NASA astrophysics mission will help us find many more.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across the whole sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
During its 2-year survey, TESS will look for signs of planets, ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds, or exoplanets, using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TESS can detect those subtle dips and even use them to determine some basic features of the planets, such as their size and orbit. Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky, called an observation sector.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
TESS will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS will fly in a highly elliptical orbit that maximizes the amount of sky the spacecraft can image, and is carefully timed with the orbit of the Moon. It will spend most of each 13.7-day orbit collecting data, and then, as it passes closer to Earth, it will transmit that data to the ground. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets. Since most of the exoplanets found by TESS will orbit bright stars, missions like Webb will be able to measure the spectra of starlight absorbed by the planet's atmospheres, which can indicate what they're made of. Ground-based measurements of the TESS exoplanets can determine their masses. Combining the masses with TESS's size measurements reveals densities, allowing scientists to better understand the exoplanets' compositions.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Kepler. So TESS is going to take that same search approach but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when searching for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at things like planet composition and atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are even further away and in deeper parts of the galaxy as well.
TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own.
You just heard a little bit about TESS's 4 cameras, and they're definitely not your average cameras. Our Amanda Griffin is live with Natalia Guerrero of MIT with more on the anatomy of a planet hunter. Amanda?
Thanks, Marie. So Natalia, you were part of the team that put the cameras on board today's spacecraft. So what was it like to watch the launch today?
It was incredible. It was so emotional to see the payload that we worked on, these 4 cameras, over the course of many, many months, and to see them go up into space and disappear, and now they are heading towards the final orbit for TESS. It's a big deal. It's really exciting, and I can't wait to get started on collecting data.
I'm excited for you. And I know you have a lot of teammates here, so tell us a little bit about the team that put these cameras on board.
Right, so the cameras were designed and tested at MIT and MIT Lincoln Lab, and so once the camera testing was complete after the course of many months, we shipped the cameras down to Orbital ATK in Dulles, Virginia, where they were integrated onto the spacecraft bus.
So what makes these 4 cameras so awesome that are on board TESS today?
So TESS's 4 cameras are tiny but mighty, is what we like to say, and they're only about 4 inches across, the lenses, and then they can fit in a mailbox basically. But they're so powerful. The lenses on these cameras are these wide-angle lenses that you can have an entire constellation like Orion in the field of view of one of these cameras.
And how far? I understand it's different than Kepler. They're studying stars closer to us. About what range are we looking at?
So TESS is going to look at near and bright stars to ourselves, and so this is stars within the range of 30 to 300 light years or so, whereas Kepler looked at stars that were in the range of 300 to 3,000 light years.
And is there anything else interesting? I think you were talking about the lenses maybe and things like that are really unique for these cameras.
Yeah, so the TESS lenses look in the wavelengths from green to really red, which is optimized to discover small planets around small stars, which tend to be redder. And the sensors for these cameras are very sensitive. So this is much more sensitive than, for example, your camera phone. So the sensitivity you can imagine, an analog here on Earth would be about the amount of light that a moth blocks out when it passes in front of the full moon.
That's awesome.
Yeah.
So can you use these cameras here on Earth?
Yes, so actually in the lab when we were testing the cameras for the first time and we received a prototype, we had it in its test chamber and we blocked the window for the chamber and left just a little pinhole for light to come in, and we were able to have people stand in front of the cameras and take a selfie.
Oh, that's probably the best selfie ever. And I think we also have a shot. You guys went on a roof at MIT?
Yes, so TESS, we took one of the prototype cameras again in a test chamber that simulates the conditions of space, that it's a cold vacuum, and took it up onto the roof of a building at MIT. And MIT in Cambridge has a lot of light pollution, but we were still able to take an image of this field that had all of these stars, and it was this beautiful dense image of all of these beautiful stars, and the images are only going to get better now that we're heading to our orbit.
Right, and I can't wait to see them. So congrats on launch today, and
thank you.
Good luck.
Thank you.
Back to you, Marie.
Thanks, Amanda. TESS will track down exoplanets ranging from Earth-sized to gas giants, orbiting a wide range of stars with different orbital distances. NASA Edge's Blair Allen sat down with TESS project manager Jeff Velosin to understand how to detect planets that are light years away. Blair?
We're here at NASA Goddard Space Flight Center with Jeff Velosin, the project manager for TESS, the Transiting Exoplanet Survey Satellite. Jeff, this is a very exciting mission looking at exoplanets. Tell us, what is the TESS mission?
So it's another mission in NASA's effort to learn more about planets outside our solar system. So it's kind of an evolution, right? When I went to college, there was no such thing as an exoplanet. One had never been found. Nobody thought there'd ever be one found because they're so small compared to the stars that they go around. So when the Kepler mission flew, maybe 10 or 15 years ago, all of a sudden thousands of exoplanets were discovered, that there were these orbiting planets around stars outside the solar system that some of them were as small as the Earth even. So Kepler was able to find planets mostly larger ones, and they focused on one area of the sky. So for years, they just looked at one area. So we knew that there's now lots of planets, and probably everywhere you look, there are lots of planets. So our mission is a survey mission. So the TESS has a survey word in it. And survey is all about, we want to look through the whole sky. So we're not going to just look in one spot. We're going to look all around the sky over a 2-year period and look for planets. We have very sensitive cameras. We're going to look for Earth-like planets that are closer to Earth. Right. Now, by being closer to Earth, it allows further follow-up study. Because if you could find planets orbiting stars that aren't that far away, now the James Webb Telescope, with its big, powerful mirror, can say, okay, I know TESS has told me there's a small Earth-like planet around that nearby star. I'm going to go ahead and focus my powerful telescope. And what happens now is when the planet goes in front of the star, you can actually see the light going through the atmosphere, coming to Earth, and then the spectrum of that atmosphere is available. And the spectrum being what parts of the starlight were absorbed by the planet's atmosphere. And that'll tell you, is there carbon dioxide in the atmosphere? Is there oxygen in the atmosphere? So all of a sudden you can learn about an Earth-like planet and what atmosphere it has. So
is TESS then really sort of putting out this map of potential planets for James Webb?
Yeah, exactly. Exactly. So that's where we fit in, right? So Kepler proved that you could find stars almost anywhere you look that have planets around them. Kepler showed that there's a variety of different types of solar systems that we never would have imagined, and that there are Earth-like planets out there. Now with a very sensitive set of cameras on TESS, we have 4 cameras on the spacecraft that'll look out at a wider swath of the sky, and then every month or two we'll move and look at a different part of the sky. But one thing we're going to focus on is looking straight up. Think of it as a north ecliptic pole, and that's a place where the James Webb Telescope can stare at that spot with the sunlight not getting in the way of the observation. So that's a place they would like to look for exoplanets, because if you're going to look at the atmosphere of one of these exoplanets, you have to stare for quite a long time every time the planet goes in front of the star. So it's great if they have these objects available straight up in the north ecliptic pole or straight down. So that's a lot of our focus. And so the goal is to find them candidates to look at.
And it seems like this is vastly different from Kepler in that it is doing this complete, I don't know, 360 full range. I don't know how to describe it.
Right, yeah, the whole sky survey. Yeah. And the great thing about that is, imagine what Kepler was able to find just blew everybody's minds. Planets that might be all diamond, planets that might have totally water surfaces. Imagine what we'll find when we now look all over the place. Kepler looked at one little area and found all that. We can't even begin to think about what are we going to find in the survey over a couple of years. So yeah, that's the exciting part about it. And the other thing is, what we'll find out is how big these planets are. So when you see the light being blocked, all you can tell is the size of the planet compared to the star. You can't tell how heavy it is. And if you can't tell how heavy it is, you really can't tell what it's made of. So what we're going to do is ground telescopes can actually look at those same targets. They look at the planet's effect on the star. So you think about TESS as looking at light being blocked. Well, what the ground telescopes are doing is the star is wiggling a little bit as it's spinning around because the planets are tugging on it. The heavier the planet, the more it tugs on the star. That wiggle is really small, but those ground telescopes could quantify the wiggle and then tell you how heavy the planet had to be. Wow. So now you have the size of the planet and the heaviness of the planet, and you can get the density and figure out, is it water, is it solid, is it gas?
Earth-like would be fantastic, but if we find, say, a desert planet, is there, what is the likelihood that we can just go ahead, name it Tatooine, and be good to go? Yeah,
there's a lot of people who are looking for, name your favorite sci-fi movie, right? A lot of people are looking for their favorite sci-fi movie planet, but I think we're going to find that there's probably even more diversity than sci-fi writers have ever thought up, and I think that's already what we've seen from Kepler, is that there's some really weird planets out there. So I think that's what we're looking forward to.
TESS will look specifically for planets with the right makeup to support life. NASA's Stephanie Martin has more on how scientists will use the TESS data.
I'm here with Paul Hertz, director of NASA's astrophysics. Now, Paul, can you tell me a little bit about NASA's search for life in the universe and how it's evolved over time?
Well, the first exoplanets, planets around other stars, were discovered with telescopes on the ground. But it took NASA's Kepler Space Telescope to show that almost all the stars in our galaxies are likely to have families of planets around them. And with the Hubble and Spitzer telescopes, we were able to start sampling their atmospheres and learning something about what they're made of. With the TESS satellite, we'll be able to find planets around the nearest stars to the sun.
It's fascinating. Now, why are we searching for life?
Well, humanity has always wanted to know whether we're alone in the universe. With TESS and the other NASA space telescopes, we can find nearby exoplanets and then study them with large space telescopes like Hubble and the James Webb, look for signs of habitability on those planets or even signs of life in their atmospheres.
Now, you mentioned habitability, and I've heard the term habitable zone. What is a habitable zone, and does that mean that there's no chance that life would exist outside of that habitable zone?
Well, we know that in our own solar system, the Earth is very conducive to life. It's a rocky planet, and it's a very balmy temperature where liquid water can exist. Planets like Mercury are too hot. Planets like Jupiter are both big and gaseous and too cold. So we want to find planets which are rocky and are in the Goldilocks zone of their star. We call those habitable planets. We're looking for those because on those planets we know that life as we know it could exist.
Now, what's next after TESS? What are the next steps to find life?
Well, NASA's next large space telescope will be the James Webb Space Telescope. We'll be launching that in 2020, and it'll be able to study some of the planets discovered by TESS and look for the gases in their atmospheres. Will they have gases like carbon dioxide, methane, oxygen, or water vapor? Gases that on Earth are indicators of life. And after that, we're going to launch the Wide Field Infrared Survey Telescope. It'll have a special instrument on it, a coronagraph, which will be able to let us measure the light directly from a planet without being obscured by the light from the star. That'll let us take the next step in exoplanet studies.
Now, what drives you personally to study these exoplanets?
Well, I think we're all interested in knowing as much as we can about the universe, and whether we're alone in the universe has always been an interesting question. It's really fortunate that today we're at the beginning of that journey. We've only known there were planets around other stars for 25 years, and now we're putting in space the kinds of telescopes that can let us study them in detail. I think that the exciting thing about the TESS mission is after TESS has discovered planets around the brightest stars, you'll be able to go out in your backyard and point to a star in the sky and say, I know there's a planet around that star. I wonder if there's life on it.
That's pretty spectacular. Thank you so much for your time, and we'll go back to you in the studio.
TESS's main goal is to find small planets with bright host stars in our solar neighborhood. This will open the door for scientists to perform detailed investigations of the planets and of their atmospheres. NASA Edge's Chris Gersh met with Stephen Reinhardt of NASA's Goddard Space Flight Center to learn more about the science behind spotting potential Earth-sized planets.
We're here with Stephen Reinhardt, the project scientist for TESS. How you doing, Stephen?
Not too bad.
What's TESS all about?
Well, TESS stands for the Transiting Exoplanet Survey Satellite.
Okay.
And it's NASA's next Explorer mission, being led out of MIT. And it's designed to actually search all of the bright nearby stars, or nearly all of them, looking for signs of planets, exoplanets. In fact, what it's looking for are transits. It's looking for those events where a planet passes in front of its host star, blocking part of the light, and that gives us this little change in the brightness of the star that tells us that a planet is there.
How are you able to detect that transit from millions and millions of miles away? Because when we've seen the Venus transit, when you see that pretty up close with binoculars, you can see it even live, but how can you see something millions of miles away?
Right, well, the Venus transit is a perfect example.
Okay.
When you watch that, if you watch a video from some of the other NASA missions, you can see this black spot passing across the face of the sun. Mm-hmm. Well, now imagine that the sun were just farther away. You don't see the spot anymore. You can't resolve it with binoculars or a telescope or anything else that we've got right now. But what you can do is you can see that star gets so very little fainter. Okay. For instance, if you have Jupiter passing in front of our sun, you see about 1% of the light from the star gets blocked by Jupiter. Okay. So if you were watching that star very carefully and were very, very far away, you would see that the light just suddenly drops and then comes back again. Okay. And so that's the signal we're looking for. We're looking for that little drop in brightness, and we're looking for it to happen regularly, right? If you, for instance, have Earth around the sun, once every year, it would pass in front of the star and block that light. So you're looking for this repeated small change in the small dip in the brightness of the star.
So given that, looking at the brightness, I mean, you have to have pretty sensitive cameras to be able to detect that dip.
That's right. So, you know, I said Jupiter's 1%. Earth around the sun is 1/100th of 1%, or 100 parts per million.
Wow.
So What TESS is designed to do, those cameras are designed to be exquisitely sensitive so that we can detect things that are small changes less than 100 parts per million. And really the thing that dominates a lot of the uncertainty are the stars themselves. Stars are not quiet at the tens parts per million level. So you've got this stellar noise, and then you've got the sensitivity of the cameras, but together we should be able to detect small Earth-sized planets around stars like the Sun and even smaller than the Sun.
Now I understand you're going to be looking at something like 200,000 stars in that 2-year mission. Are you picking out those stars, or are you just kind of going to a region and say, look, we're just going to look for opportunities in a certain region?
So it's a predetermined list, except where it's not. Most of this list there's a group of the science team that have worked on a thing called the TIC, the TESS Input Catalog. Okay. And the TIC has about 3 billion stars, if I remember my numbers correctly, in it. Obviously, we're not going to be looking at all those. Right. It's every bright object in the sky down to a certain brightness level. It's huge. But then there's the actual target list. And that's between 100 and 200,000 stars. And these are stars that are specially selected for specific observations with TESS using a 2-minute cadence. So every 2 minutes, they measure the brightness of that star. Okay. And those are the stars that have the highest likelihood that we'll actually be able to find an Earth-sized planet around them. So stars that are smaller, it's easier to find smaller planets around smaller stars. Right. Stars that are brighter, and so on. In addition to that, there are additional stars that are proposed by members of the general community through the guest investigator program, and that means that we can observe some other stars that were not necessarily viewed as great targets by the science team, but which somebody out in the community says there's a good reason to look at this star, so we will. And in addition to that, we have the full frame images. So every 30 minutes, TESS takes a picture of the entire field of view, which is 24 by 96 degrees. Wow. It's huge. And with that, we're going to be able to find a lot more planets. Now, most of those planets are going to be the large planets. They're going to be Jupiter-sized planets and so on. But it's about 10 times as many of those in the full-frame images than the number of planets that we'll find in those postage stamp data, which are really focused on trying to find the smaller planets.
Now, look at our solar system. Our sun is an average star. Are you kind of targeting those type of stars for possible Earth-like planets, or could you have stars that are much bigger than our sun that could potentially have an Earth-like planet?
So, first off, let me say that when we say that our sun is average, we're really wrong. Our sun is actually kind of unusual. It is a sort of average in size, but it's not actually very active compared to most stars. Oh, wow. And there's a lot of other stars out there that are very, very different. So a lot of the stars the TESS will observe are what we call the M dwarfs. So these are much smaller than the sun. Okay. They're much cooler than the sun. So for instance, the habitable zone, that region around the star where you could have liquid water on the surface of a planet, is much, much smaller than you have around the sun. Those are going to be very good targets for TESS because they're smaller. Okay. The larger stars, if you start talking about some of the stars that are a few times bigger than the sun, the problem is that now trying to find a small planet around this big star, it gets really hard. So, imagine that you have a star that's 3 times bigger than the sun, but you have that same planet, then suddenly it's 1/10 of the as easy to detect as it was before. So while we will look at some of those, it's going to be really hard to find the smaller planets around those kinds of stars. But those are important observations to make because we haven't done a lot of observations of those larger stars looking for exoplanets yet because they're hard. And so we really don't know what the population of planets looks like around those kinds of stars.
Final testing of the TESS spacecraft was done right here at Kennedy Space Center. That happened in the Payload Hazardous Servicing Facility. NASA Edge's Franklin Fitzgerald had a chance to see the spacecraft in the clean room and talk with Orbital ATK's Robert Lockwood.
Hey, today I'm hanging out with Robert Lockwood, who is the spacecraft program manager from Orbital ATK for TESS.
Hey, Franklin.
Hey, man, we are going to go over to this big building. Is this a high bay or a clean room?
Yeah, it is. It's a big high bay clean room. It's the Payload Hazardous Servicing Facility.
Once I get in there, I'm going to do a little bit of a B-roll for our show, but also we'll have an opportunity to do an interview.
Okay.
Do I have to put on a bunny suit?
Yeah, you do. You're going to get all covered up. The main source of contamination for spacecraft is people. So we're going to cover you all up in a bunny suit, going to put a mask over your face, but you'll still look pretty.
Oh, I'm glad I saved lunch for after the interview. So Robert, we're here in this high bay clean room. What types of tests or checkouts are done for tests in this facility?
Well, primarily in this facility is for propellant fueling. We're going to fuel the vehicle with 45 kilograms of hydrazine to perform our on-orbit maneuvers. This facility is certified for propellant fueling, so that's primarily why we're in here. We also have other performance tests that we do. Check it out after it went from Dulles to here, make sure everything worked after shipment, deploy the solar arrays and stow them. We also do a number of checkouts and closeouts. One of the things they're doing today is putting the vehicle on a high stand so that we have easier access under the vehicle to close out some of the parts on the bottom part of the vehicle. When our partners from SpaceX arrive here with the fairing, we will attach the vehicle to the fairing, encapsulate it, and then they will transport it over to Space Launch Complex 40 for launch.
As the program manager for TESS, tell me about some of your duties.
Primary among those are moving all the little parts around, the logistics for keeping things on schedule, keeping staff working in the areas they need to, interacting with all of our partners at MIT, at Goddard Space Flight Center, to make sure that things just keep moving smoothly towards launch.
See, when you talk about partners, you've received components for tests from all over the country, but when you talk about MIT, they are responsible for pretty much the major part of the satellite, the cameras, is that right?
That's right. So we have one instrument. It's comprised of 4 wide field of view CCD cameras. Those are manufactured at MIT Lincoln Laboratory and then delivered to us for integration.
And integration was done at Orbital in Dulles, Virginia, right?
That's right. We have a full facility there for integrating all the parts and testing it.
Talk to me a little bit about the testing. I know that there is environmental testing done for all satellites. Can you tell us a little bit about the process that TESS went through at Orbital?
Sure. We received the 4 cameras sitting on its camera plate and integrated it to the top of our spacecraft bus to form a full observatory. Then we take it through a set of comprehensive functional tests just to make sure that everything is working correctly. We then put it on a shaker table or vibration facility where we shake it at levels that simulate launch environments. We put it in a chamber to test it for electromagnetic compatibility. Then we put it in a thermal vacuum chamber to expose it to the highs and lows, hots and colds of on-orbit environments.
Robert, did you encounter any obstacles along the way managing this program?
None to really call out. It's the typical thing when you put spacecraft together in a facility like Dulles, Virginia. There are a number of spacecraft processing through there. So it's a continual shell game when your part is ready to go integrate or when your part's ready to go onto the vibe table for test or into the TVAC chamber. But no obstacles that really stopped us from getting here on time. And in fact, we've got about 3 weeks of margin to sit around now. So we're actually even a little early.
Yeah, well, yes, when I was in here shooting some B-roll, TESS was uncovered, but now it's bagged. So I'm assuming you're pretty much on the back end of everything you need to do.
We are. We're bagging it to keep her safe for about 3 weeks while I let my staff go back to Virginia and see their family. And we'll keep one person down here just periodically checking on her, but she's just going to sit there and wait. But then we will come back in 3 weeks' time, take the bag off, and continue on processing.
TESS is almost ready to open its solar arrays or wings to power the spacecraft. Let's go back to Josh and Mike to take us through the deployment. Guys?
Hey, Marie, thank you. We actually are about 3.5 minutes away now from the second stage engine burn number 2, which is a burn that'll last a little less than a minute, Josh. And when it ends, it will place TESS in the right position for deploy into space. And that just is the beginning of the journey. We'll have more information, and we'll be back to fill you in on when the burn takes place.
The launch happened on time today at 6:51:30. It was a beautiful launch. Weather cooperated with us today. No chance of precipitation, no clouds in the sky. It was really a beautiful launch.
Absolutely.
TESS will search the sky for telltale signs of exoplanets or planets looking for other stars. TESS will survey nearly the entire sky, and we have a video to tell you more about that.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. Led by MIT, TESS will find thousands of new planets orbiting nearby stars. During its 2-year survey, TESS will watch a wide variety of stars, looking for signs of planets ranging from Earth-size to larger than Jupiter. Each of TESS's cameras has a 16.8 megapixel sensor covering a square 24 degrees wide, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a long strip of the sky called an observation sector. TESS will watch each observation sector for about 27 days before rotating to the next. It will cover the southern sky in its first year and then begin scanning the north. TESS will study 85% of the sky, an area 350 times greater than what NASA's Kepler mission first observed, making TESS the first exoplanet mission to survey nearly the entire sky. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets, expanding our understanding of worlds beyond our own.
Okay, we are a little bit more than a minute away from the expected restart of the SpaceX Falcon 9 second stage Merlin engine. This burn once again will last under a minute. It will place the TESS spacecraft in the proper location to be deployed into space to begin its journey. Looking live now at the second stage engine, at the Merlin engine. We're expecting the burn to begin in about 30 seconds. Second stage, along with the TESS spacecraft transiting across the globe, having passed out over Africa. Liquid oxygen tank being pressurized for the burn. Fuel tank coming up to pressure for the burn. This is the Launch Vehicle Data Center inside Hangar AE on Cape Canaveral Air Force Station, where the team of TESS awaiting information on the second stage burn. Expecting the second stage burn momentarily.
Evac ignition.
And we have ignition of the second stage Merlin engine. This burn is planned to last just under a minute.
Everything proceeding normally on the burn? About 10 seconds remaining in this burn.
And the second burn of the second stage Merlin engine has shut down. You can see the red glow cooling.
GNC confirms nominal orbital insertion.
And the second stage burn is complete. The second stage continues, as you can see on your screen there. And with now, we will go to a video of Stephanie Martin, who is going to help you learn a little bit more about how we find exoplanets around habitable zones, the Goldilocks zone of stars. We'll go to that video now.
I'm here with Doug Hudgens, the program scientist for exoplanet exploration. Doug, thank you so much for joining me.
Thank you for inviting me.
Now, can you tell me a little bit about why we study exoplanets?
We study exoplanets because we want to understand first just how planets form and evolve, what the whole exoplanet zoo looks like. Because our own solar system has the 8 planets that we know of, but in fact, finding other solar systems, we find other planets, other types of planets that we maybe don't have in our solar system, but we also find planets that are arranged in different orders with gas giants close to their star and other planets further away. And all of that tells the story of how planetary systems come to be. The TESS mission basically uses the transit technique to detect exoplanets, which means we watch many stars and look for a tiny dip in brightness that occurs each time a planet orbits and passes in front of the star. Now, when TESS detects a exoplanet transit, really that's just where the science begins, because there are also things out in space that can mimic or might fool us into thinking that there's an exoplanet around the star when in fact it's something else entirely. So the first thing that we have to do is we go to ground-based telescopes. Members of the science community, certainly the TESS science team, will be very involved and very active going to ground-based telescopes, carrying out observations of those transiting systems to kind of rule out the astronomical false positives that might trick us.
Now, how can citizen scientists and amateur astronomers help look for these exoplanets?
Well, this is really exciting. The nice thing, the great thing, the exciting thing about TESS is that it is going to be looking at the nearest and brightest stars to the Earth. Now, its predecessor, the Kepler mission, which did a fantastic job in discovering a huge number of planets, most of the stars that it looked at were very faint and largely beyond the grasp of amateur-sized telescopes. TESS is looking at stars that are going to be brighter and much more accessible to ground-based observations and to amateur telescopes. So scientists that have a good quality telescope are going to be able to themselves contribute by carrying out observations of these systems just simply because they're more amenable to their equipment.
Now, how do these amateur astronomers get involved?
There are a number of citizen science opportunities out there. They can actually get in and look at data and help scientists dig out some of these transit signals, because in the TESS data, we are going to be looking at the light from millions of stars, more work than the science community can ever hope to do themselves, and we'll really be looking forward to help from the general public.
Thank you so much for joining me. I really look forward to hearing more as you get the data back from TESS and scientists across the world are able to really delve into it.
Thank you.
Thank you. Back to you.
And we are back once again at Hangar AE, looking in the Launch Vehicle Data Center, where the TESS team awaits test deploy from the SpaceX Falcon 9 second stage, anticipated in about 45 seconds. Everything so far today has been going very well, on time. The TESS mission is just beginning, but so far so good, as the second stage continues to carry TESS in an orbit to the precise place in space for the deploy. Looking at the second stage Merlin engine, and now looking forward from the second stage of the Falcon 9 rocket.
Payload deploy confirmed.
And confirmation of payload deploy. You can see the TESS team there, excited to see the spacecraft, the Planethunter, flying free.
So with the successful deploy of the TESS spacecraft, the next major milestone is the beginning of solar array deployment. That activity is expected about 8.5 minutes after spacecraft separation. So in about 7 minutes from now, we'll of course be back to join the beginning of that. That process will take about 20 minutes to complete. We'll rejoin in time for you to track the deploy of the solar arrays from the TESS spacecraft.
TESS will fly in an orbit that completes 2 loops around the Earth every time the Moon orbits once. This special orbit will allow TESS's camera to monitor each patch of sky constantly, for nearly a month at a time. To get this into orbit, TESS will make a series of loops to build momentum. Then, the Moon's gravity will push TESS to its final orbit, 60 days after the launch. Here's another video to tell you how that works.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. Led by MIT, TESS will find thousands of new planets orbiting nearby stars. To accomplish this, TESS will fly in a special highly elliptical orbit that maximizes the amount of sky the spacecraft can image. Once TESS has launched, it will expand its orbit until it can get a gravitational assist from the Moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the Moon's orbital plane. TESS orbits Earth in exactly half the time it takes the Moon to orbit once. This feature helps stabilize the spacecraft's orbit against tugs from the Moon's gravity. TESS will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, TESS will rotate and transmit all its accumulated data to scientists on the ground. Over 2 years, This will allow TESS to study nearly the entire sky and potentially find thousands of new exoplanets.
We're 53 minutes, 41 seconds since the launch of the Falcon 9 rocket carrying the TESS spacecraft. Successful first and second stage burns have placed TESS into its proper location in space. It's been deployed from the Falcon 9 second stage. Solar array deploy is an activity that is expected to take about 20 minutes from the time of spacecraft separation. Here at Hangar AE on Cape Canaveral Air Force Station, TESS controllers are monitoring the spacecraft, reporting on acquisition of telemetry. They'll be looking for power positive indications from the spacecraft. We're expecting the beginning of solar array deploy on the TESS spacecraft in about 2 minutes, 57 minutes, 58 seconds after liftoff.
And we are just under a minute away from the start of the solar array deploy. The spacecraft is now sun-facing.
Acquisition of signal, Auckland.
And we have just received successful deployment of Wing 1 of the solar arrays of the TESS spacecraft. And you can see clapping there from the TESS team, confirmation of the second wing of the solar array has successfully deployed. TESS will spend the next 60 days getting to its proper orbit to do its primary science mission to find exoplanets outside of our solar system.
A very successful day today for NASA and SpaceX. In the beginning of the TESS mission, liftoff of the SpaceX Falcon 9 rocket occurred on time at 6:51 and 30 seconds Eastern Time. The first stage engine did its job, handing off to the second stage engine, which performed 2 successful burns to place the TESS spacecraft in a proper location in space, at which point deploy occurred, followed moments later by the solar array deploys. So at this point, the TESS spacecraft is acquiring power. Telemetry is being read. And a lot of happy people at Hangar AE watching the beginnings of a very successful TESS mission, Josh.
Yes, TESS, the Transiting Exoplanet Survey Satellite, is led by the MIT team. TESS will find new planets orbiting nearby stars. To accomplish this, TESS flies in a special highly elliptical orbit that maximizes the amount of sky the spacecraft can image. TESS will expand its orbit until it can get a gravitational assist from the moon. This slingshot will move it into a stable orbit that is tipped about 40 degrees from the moon's orbital plane. TESS orbits in exactly half the time it takes the moon to orbit once. This feature helps stabilize the spacecraft's orbit against the tug from the moon's gravity. TESS will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, TESS will rotate and transmit its accumulated data to scientists on the ground. Over 2 years, this will allow TESS to study nearly the entire sky and potentially find thousands of new exoplanets.
One hour, 9 minutes after the launch of SpaceX Falcon 9 and the TESS spacecraft, everything has gone so amazingly well, Marie. The rocket launch performed well. The spacecraft has been deployed. Solar arrays are deployed. And with that, we'll turn things back over to you.
Awesome. Great to see that all come together. Thanks, Mike. Let's go now to NASA Edge's Franklin Fitzgerald. He is standing by live with TESS's Deputy Project Manager for Resources. And Franklin, I understand it's a pretty celebratory mood over there.
Yes, it is, Marie. I'm here with Matt Ritzko, who, as you said, is the Deputy Project Manager for Resources for TESS. And Matt, you've been with TESS since it was a stack of papers on a desk. And today you've seen a successful launch. And as Marie said, it was a celebratory, it was applause, it was elation going on in the control room after the solar arrays deployed. Tell us a little bit about how you feel right now.
I'm trying to catch my breath. So thanks, Franklin. I mean, you guys do an awesome job, so thanks for giving us the time today to come and talk. But I just came out of the control room, and we had several rounds of applause. So first we had the launch, and all of us ran outside, and then we came back in, and then we saw the separation, and then we applauded then, and then we had telemetry from the spacecraft, and that instrument team applauded, and then we had spacecraft solar array deployment. So very exciting. It's just the series of things that take place to have a mission enter an orbit and be successful.
Now, the solar array deployment is a major milestone. Tell us about that operation and what it means for the mission.
So it means, from a TESS perspective, TESS is a very simple satellite by NASA standards. There's only one deployment. It's our solar arrays. It's an explorer's mission, which means it's a fast-paced development from soup to nuts, and it's usually lower cost for NASA. So we try to make it as simple as possible. So the only deployment we had on orbit were the solar arrays.
Now, the solar arrays are used for power for the satellite. Now, I assume that it was running off of batteries until the solar arrays deployed. Tell us how they work with the satellite moving forward.
So when we are inside the fairing, the team has batteries that are charged up, and we turn them on, and we put the spacecraft on internal power. Once we launch, the fairing separates, and we have to get the arrays open within a certain period of time, get them pointed to the sun, and then start charging our own batteries again. Without that, if solar arrays don't deploy, you could lose a mission. So for us, it's very important for that process to take place and to turn on all the power on TESS, to start getting all our instruments turned on. So now we're on our own power, and we're flying in space. It can't get any cooler than that.
What are the next moves for TESS moving forward?
So within the next few weeks, TESS is a little more unique. We have 6 burns. TESS has a small thruster on the bottom of it. We'll burn in a highly elliptical orbit. It's a little unique for TESS. And we'll actually do a lunar flyby around May 15th, May 16th, and eventually we'll achieve our final science orbit in June 16th or 17th. And then at that point, we'll be in full-on science operations. So over the course of the next several weeks, TESS is going to be making these maneuvers to get to our orbit. And what makes it so unique is that's how we get the most science from TESS that we possibly can.
Well, Matt, thank you for giving us a little bit of your time this evening. I know that you have to get back to work, but we appreciate you coming in and doing the interview for us.
Absolutely. Thanks for having me today.
All right. Marie, back to you all in the studio.
All right, thanks, Fitzgerald. We want to hear now from the Launch Services Program Manager, Tim Dunn. He's with Josh in the Mission Director Center. Josh, are you there?
I'm here, Marie, and I'm actually here with Tim Dunn as well, the Launch Services Program. Tim, can you tell us about how today's launch went?
Hey, Josh, wow, are we excited? I mean, we just had a perfect countdown and perfect launch of the TESS mission. It was a wonderful day. Obviously, if you got any views outside here off the Central Coast, you saw what a gorgeous day it was. So we had perfect weather for the launch. We had a terrific rocket. The Falcon 9 just continues to demonstrate what a reliable ride it has become. And spacecraft, we turned on TESS spacecraft early this morning, and that went super smooth. We worked one very minor little item with TESS during the countdown. Was really insignificant in the overall picture. TESS was really solid during the rest of the countdown, and the range. Hats off to the United States Air Force and the 45th Space Wing. They continue to have a beautiful range for us to launch on. And again, I don't have a whole lot to talk about as far as troubles during the countdown. It was super smooth, beautiful day, a beautiful launch, a great rocket, and we now have an operational spacecraft on its way to do great science.
And talking about the importance of the TESS mission, can you talk about from the perspective of the Launch Services Program, how it is to launch TESS?
Oh, wow. Well, for us, this was only Launch Services Program's second flight on a Falcon 9 rocket. A couple of years ago, we did the Jason 3 mission from the West Coast, and so this was our second full-up science mission on Falcon 9. So our entire team of engineers and analysts within LSP was able to demonstrate another certification process where we certified this full thrust version, Block 4, that flew today. And to see all of that hard work for the past 2.5 years that the entire Falcon 9 team within LSP put together, to see that rewarded with a successful launch means so much to our team. And it's an incredible team. And SpaceX has an incredible team. Their engineers and analysts here at the launch site here at Cape Canaveral, as well as their team back in California at Hawthorne. My hat's off to them. Terrific launch team. And when you put us all together, the government and the commercial guys together, it's just so satisfying to watch a team kind of seamlessly blend and integrate to accomplish such an important mission for our agency.
So it sounds like a pretty exciting night for both SpaceX and NASA. And the Launch Services Program has a big year, and we've got big stuff coming up still. Can you tell us about what's next for the Launch Services Program?
Absolutely. So we were thrilled to launch tonight, mainly because now it kind of clears a little bit of the runway, because our Atlas V team now has to turn around, get out to the West Coast for the InSight mission, flying in just 2.5 weeks on May 5th from Vandenberg Air Force Base. And then we have a Pegasus mission coming up with the Icon spacecraft, and that's going to stage out of Vandenberg, fly downrange to Quaj, and launch from Quaj in mid-June. Right now we're targeting June 14th. We come back here to the Cape in the end of July. We'll be processing the Parker Solar Probe mission, which is a mission to go study the sun. And it will be the first time LSP has flown a science mission on the Delta IV Heavy. So that's very exciting for our team. And then if all goes according to plan, our 6th and final mission for LSP for 2018 will occur in September from Vandenberg Air Force Base again, and that will be the ISAT-2 mission on the very last Delta II launch vehicle. So I would say if you're a Delta II fan out there, you might want to find your way to the Central California coast right around September 12th, because that's going to be a very special event to watch the final Delta II fly. It's been a workhorse for the agency, and it's really special to a lot of folks that have been in this business for the last 30 years now that it's been flying.
Well, it sounds like we've got a lot to look forward to from the Launch Services Program, and then a lot to look forward to with the TESS mission, which we launched successfully tonight. So with that, we'll sign off and go back to you, Marie. Thank you.
All right. Thanks, Josh. This concludes our live coverage of the successful launch of the Falcon 9 and TESS, the start of a new period of discovery for NASA and the world as we search for more planets and life in space. For more information about the TESS mission, visit nasa.gov/TESS. I'm Marie Lewis. From all of us here at Kennedy Space Center, thank you for joining us. We will leave you now with replays of today's awesome launch. Have a great night.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Radiate from the engine plumes to counter the effect of vibration.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Radiate from the engine plumes to counter the effect of vibration.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. From the engine plumes to counter the effect of vibration.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Status of stage 1.
Stage 1 propulsion nominal. Go.
And we have confirmation.
Stage
Main
separation
mission cut
confirmed.
off.
And stage confirmation is confirmed.
You're looking at a live shot of the second stage single.
Stage 1 is energy flip.
And the second stage Merlin engine has ignited.
Standing by for fairing jettison. That is protected TESS on its way through the atmosphere. Just seconds away from jettison.
Seven, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Status of stage 1.
Stage 1 propulsion nominal.
SpaceX Falcon 9 is
Power telemetry nominal.
mechanical stress on the rocket reached its peak.
Vehicle is supersonic.
And the vehicle is supersonic. Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket, the status of Stage 1.
Stage 1 propulsion is nominal.
And the SpaceX Falcon 9 has begun the pitch kick maneuver. Just about 45 seconds into flight of the Falcon 9.
Power and telemetry nominal.
Just over 1 minute, the Falcon 9 will reach transonic speed and pass through max Q. That's the point where mechanical stress on the rocket reaches its peak.
Vehicle is supersonic.
And the vehicle is supersonic. Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket, status of Stage 1.
Stage 1 propulsion is nominal.
The SpaceX Falcon 9 has begun the pitch kick maneuver. Just about 45 seconds to flight of the Falcon 9.
Power and telemetry nominal.
Just over 1 minute, the Falcon 9 will reach transonic speed and pass through max Q. That's the point where mechanical stress on the rocket reaches its peak.
Vehicle is supersonic.
And the vehicle is supersonic.
Vehicle has passed maximum aerodynamic pressure.
Just about a minute away from the next major
Engine
milestone.
chill has begun.
Main engine cut off. You'll hear the call MECO. That happens about 2 minutes, 30 seconds into the flight.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket, Status of stage 1.
Stage 1 propulsion nominal.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system. Two, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. schedule may call out some